Okay, so now we are ready to integrate the PDF of a continuous random variable to get the CDF. Okay, so what we're going to do is we're going to start with this continuous random variable, and we're going to find, so we start with its PDF, and we're going to find its CDF. So just remembering what's always true, whether we've got this particular random variable or any other continuous random variable, what is always true is that the CDF, capital F, of x is a function of b, tells us the probability that x comes out to be less than or equal to b, and we find that by taking the integral of all values up to b of the PDF of x with respect to x. Okay, so this is always what happens. Okay, but we want to do this process in this specific case here. So what I have here is uniform random variable, and I've got its PDF written here, and it is equal to a constant value over the range where it's defined. So it's equal to 1 over d minus c in the range from c to d, and it's 0 everywhere else. And we know that if it's uniform on the interval c to d, the height of the PDF must be 1 minus d over c, because that's what we need for the whole area here to integrate to 1. Okay, it's a rectangle. We don't need calculus to figure out that area. It's the base, d minus c, times whatever height will make the area equals to 1, and that height is 1 over d minus c. Okay, so let's take that particular information, that information about this particular PDF, and work it through the CDF process. Okay? So the integration is going to be pretty easy here. There is this business of having to deal with the other parts of the CDF, the parts that don't have any probability assigned to them. So let's just kind of be careful and systematic. And what do we have here for the CDF? The probability that x is less than b. Well, first of all, if b is less than c, it's going to be 0. Okay, right? This whole range, all these possible values of b here that are less than c, no probability. Okay, it's only defined between 0 and between c and d, so no probability that it's going to be less than c. When we're in the range where b is between c and d, that's when the probability that x is less than or equal to b is equal to this integral. And it's the integral from c up to b of 1 minus d minus c dx. Okay, so let me just comment on a couple of things here. I need to have something that I can put into I need to have a valid limit of integration here. And so the way I'm substituting c in here for negative infinity is by taking care of all those values between negative infinity and c, if you want to think about it that way, all those values less than c, that's what I should be thinking of, and noting that the cumulative probability there is 0. So that allows me to put c here for my lower limit of integration. So what I'm going to be doing here is finding for all of the values of b that are in this range, I'm going to be finding the value of the area between b and c. So here's another b, here's another b. Okay, all the rectangles that are always bounded below by c. Okay, and then once we get above d here, so when we have the case where b, back to my pen, b is greater than or equal to d, then the cumulative probability is going to be 1. And we know that because we know that the area under the whole square is 1. Okay. So that's nothing left to do but evaluate this integral. Okay, and it's not a particularly hard integral to evaluate, but let's just go ahead and do it. Okay, so the integral from C to B of 1 over d minus c with respect to x. Okay, so we're integrating with respect to x. There's no x in here, meaning this thing is a constant. So we'll find the integral. What we're asking is what function has the derivative d minus c? What function's derivative with respect to x is 1 over d minus c? Oh, that would be x for d minus c. What function has the derivative, this constant that happens to be a fraction with the difference between d and c in the bottom? Oh, x times that. So this is this function is a line with slope 1 over d minus c. And we want to evaluate, so that's, we've taken this is the indefinite integral that we found here. We've done the integration. We found the antiderivative, the function whose derivative is 1 over d minus c. And to take the definite integral to turn it into a number, we just bring along our limits of integration here. That should be a b. And so remember, the limits of integration are sort of coming from 2 different places here. This is the lower bound coming from our probability distribution, and it's letting us know information from the PDF that tells us, well, when do we start getting positive probability? Oh, it's at C. B, on the other hand, is the number whose cumulative probability we're looking at here. Okay. But once we're cranking away through the integration, they're both just numbers. So we plug them in to evaluate the definite integral. So it's b over d minus c over d minus c. So probably put that over common denominator. Okay. And that is, we're thinking about that as a function of b, which is how I've parameterized it over here. As I noted before, you could use x for all of these things, but at this particular step here, I like to have this x reminding me of what I integrated with respect to, and this one, this argument reminding me of that I'm looking for the number whose cumulative probability I seek. This is the number whose cumulative probability I seek here. Okay, and so this is indeed just a linear function in B that has, I would have a negative intercept here if we continued it down there, and it has slope 1 over d minus c. So this is another way to say it. Here's our, would normally be an x variable, slope is 1 over d minus c, and here we have an intercept that's just sort of letting us know where that line would intersect the y-axis. Okay, let's, I've got it kind of written all over the board. Let's go down here and in blue, actually, let's go just to another page and write the cumulative distribution function nicely and neatly without a lot of scratch work in between. Okay, I've got it written in shorthand in the picture, but really the full function here is got these 3 parts to it. It's got the part that is 0 for b less than c. That is b over d minus c over d minus c for b equal to c and less than d, and is 1 for b greater than or equal to d. Okay. And that is indeed the function that you see. And that, again, let me emphasize, the CDF is a number that you can plug a value for B in, and what you will get is a probability. Okay? So you will get a probability that X is any of these B's along here, it's 0. Any of these B's in this range, the cumulative probability will be increasing in B. And then once we get to D, the probability that X is less than or equal to any number greater than D is going to be 1. So there's our CDF. And we'll do another one like this in the workshop. I'll see you then.